In the high-stakes world of industrial plants, we're talking refineries, power stations, chemical factories, equipment is running under immense pressure and extreme temperatures. When something breaks, you can't just toss it out. You have to fix it safely and reliably. But how do you repair something that's engineered to be practically perfect? Well, let's dive right in, using the ASME PCC 2 standard as our guide. So today, we're going to walk through the entire engineering process for a critical repair. We'll start with the standard itself, then move on to assessing the damage, explore how to pick the right method, compare the two major families of repair, and then wrap up with how engineers prove their work is safe. All right, so our journey begins with the rulebook. In the world of pressure equipment, that means ASME PCC 2. This is the go-to guide for any repair made after a piece of equipment has been put into service. Think of this standard as the collective wisdom of thousands of engineers, all documented. It provides proven, peer-reviewed methods for everything, from the initial design of a repair to the final tests that sign off on it. Whether the fix is a temporary patch to get you through the week or a permanent solution, this document makes sure it's done right. The standard itself is laid out super logically. It kicks things off with the basics in Part 1. Then it dives into the three main families of repair: welding in Part 2, mechanical clamps in Part 3, and modern non-metallic composites in Part 4. And finally, Part 5 covers how you test and verify everything. It's a complete roadmap.
So with the standard as our guide, the next step is to understand the problem. You can't fix what you don't understand, right? That's why the first active step in any repair is a meticulous damage investigation.
Before even thinking about a repair, engineers do what's called a fitness for service, or FFS, assessment. The whole point is to ask the fundamental question: given this flaw, is the equipment still safe to operate as is? Sometimes the answer is actually yes, and no immediate repair is needed. This process follows a really clear decision path. It all starts with detecting the flaw. Then you have to understand why it failed. Was it corrosion, fatigue, an accident? Only then can you figure out the right course of action, which could be no repair, a full replacement, or what we're talking about, a targeted repair. It's a very structured process. So how do they find and measure these flaws? With non-destructive examination, or NDE. These are the tools that let engineers see inside the steel, using sound waves, magnetic fields, or just a detailed visual inspection to precisely map a crack or measure a wall's thickness without ever having to cut into the component. Okay, damage assessed. Now comes the real heart of the engineering, selecting the right repair technique from the toolbox that the ASME standard provides. And there is no silver bullet here. The perfect repair for a corroded pipe in a low-temperature system is completely different from fixing a fatigue crack in a high-pressure vessel. Engineers have to weigh all these factors: the material, the operating pressure, the temperature, how long the repair needs to last to make the right call. While there are lots of techniques, most fall into two big buckets that kind of represent the traditional versus the modern approach: welded repairs and repairs using non-metallic composites. The fundamental differences here are pretty clear. Welding is the classic approach. You're essentially reforging the metal, restoring its original strength. But it involves intense heat, which can be risky. Composites, on the other hand, are often applied cold. They're basically high-strength, engineered wraps or patches, bonded with epoxy. They're fantastic for things like external corrosion or wrapping complex shapes where welding would be a nightmare. Here's a perfect example of what that looks like in practice: a classic welded patch plate. A new piece of steel, carefully shaped to the vessel's curve, is placed over the damaged area and welded all the way around. It's a robust, time-tested solution for restoring strength.
But welding is not simple. You've got to make sure the patch material is compatible with the vessel material. The welding process itself introduces immense heat and stress into the metal, which has to be managed. And you absolutely have to perform NDE after the weld to make sure the repair didn't introduce any new hidden flaws.
So, the repair is complete, but the job is far from over. Now you have to prove, beyond a shadow of a doubt, that the fix is safe and effective. This is the validation phase.
This is the one question it all boils down to. Is the equipment safe to put back into service? And you can't just guess. You have to test it. The absolute gold standard for validation is the hydrostatic test. You fill the vessel or pipe with water and pressurize it to a level well above its normal operating pressure. If it holds without leaking or deforming, you've proven its structural integrity. However,
Subjecting an entire, massive system that's been in service for years to a high-pressure test can sometimes be impractical or even risky. That's why the standard offers an alternative, using advanced NDE in lieu of a pressure test. Instead of pressurizing the whole thing, you use techniques like ultrasound to do a deep, volumetric scan of the repair weld, proving its soundness that way. So the key is choosing the right validation method based on risk and practicality.
At the end of the day, this is what it's all about. Following a rigorous standard like ASME PCC 2 isn't about red tape. It's about a disciplined, engineering-based approach that ensures the massive, powerful equipment that makes our world run can be fixed and operated safely. And that leaves us with one final thought. As we develop new materials, new manufacturing techniques like 3D printing, and new inspection technologies, how will these essential rulebooks have to adapt? The work of ensuring safety is never truly done.